Hi everyone. Today actually we're going to continue on 9.3 surface integral. And I know my last videos I said that that would be the last video, but I decided I'm going to push one more video out for 9.3 so that I can actually give you an example on how to evaluate the surface integral using some of these different notations that you see. We will actually try to use this one with the parameterization for the surface. But I will also show you how to use this one right here for the correct format or for the correct information. This can also make it easy to integrate the surface integral. This is actually the one that we're not going to use in my example for reason that it doesn't really fit into this notation. So the idea is that all three notation for surface integral will allow you to evaluate the surface integral, provided that you have the appropriate things that you need. So in this example that I'm going to do, we will try to come with the parameterizations to form the surface integral and evaluate it. But I'm also going to make use of the fact that we know the perpendicular vector, the unit normal vector, and that actually will help us figure out what the surface integral is a lot easier in this example. So I would like to illustrate that. So I'm just going to show you what this example is. So hopefully this example is not going to take 30 minutes to go through. I really hope it's not, but I do plan to do this example twice. So it's potentially possible. So I don't know, but we'll see. So here's an example. We're going to go and start by let vector f of xyz to equal to just xyz. So a very basic vector field where it basically just take the position and just point a vector that's kind of go in that direction. So if you want to know what this vector field look like, you can imagine there's an explosion at the origin and everything get pushed away, and that's how this vector field look like. And I'm going to go and let S be the surface of a cylinder of radius A and height B. And we are going to orient all the perpendicular or normal vector to be pointing outward from the cylinder. We're going to let all normal vectors be pointing outward. And I know you're probably not sure what does that mean, so lucky for you, I have a picture. I'm just going to see if I can actually, let's see if I can insert that picture. Not what I wanted. There you go. Oops. Okay, let's see if I can put it somewhere over here. So that's basically what it is. That S would be a surface of a cylinder, and I'm saying all the normal vectors are pointing away outward from the cylinder. So if you think about it, the surface S is actually formed by three different surfaces: the bottom circle, the top circle, and the lateral area. And they each have their own different normal vector, where the bottom, the normal vector is pointing straight down, the top, the normal vector is pointing straight up, and then the lateral area, the perpendicular vector or the normal vector actually pointing outward. So the way the perpendicular or the normal vector pointing are just basically forming the orientation of the curve. So you basically want the orientation so that you can follow kind of the right hand rule when you go around the boundary of the surface that you're dealing with. And in this case, you can imagine the following. For the top, we probably need the boundary to kind of go around in circle like this. So that way follow the right hand rule where the perpendicular point upward. The bottom would be like this, which have to actually rotate the opposite direction. And then for the lateral area in the middle would actually probably go something like this. It will actually go, I would say, I don't know, I want to draw more arrow because that might be confusing. But how about I draw the arrow this way? So it will probably go like this. So you kind of go around, down, around, and up, and around like this. So that would force the perpendicular vector to go outward. Okay, imagine you can cut the cylinder open, the lateral area actually rotate out into a rectangle. That's basically what it looks like. And so you basically go around the rectangle in a right hand rule. Now, none of these are that big of a difference, so but I'll show you where would fall an impact. So here I'm going to go and say the following. We're going to let S1 be the top. So S1, let's say we're going to let S1 be the top, S2 be, oh actually S1 be the bottom, I'm sorry. And S2 be the top, and S3 be the lateral area or lateral surface. Okay. So what I'm going to try to do is to try to calculate the surface integral. So I'm going to ask you to try to evaluate a double integral over this surface S of vector f dot d vector s. So that would be our surface integral. Notice that I cannot use this notation. The reason why, because I will require me to already have a parameterization, and I can define the domain of the parameterization, which I don't have yet, but I do have the surface S already. So I have to use either this notation or this notation for now. But I will actually transform it using parameterization and evaluate it. So first thing that I notice is the following. This is actually equal to 3 separate integral. Add together. Let's see if I can squeeze this in. There you go. So we just have to calculate each one individually. So let's start with, I don't know, let's start with S1. So for S1, I'm going to have to first define a parametric representation first. So if I'm looking at this correctly, it seems to me is just a circle and its interior while staying on the XY plane. So therefore, the parameterization in this case would probably just be this. So it will allow me the z equal to be 0. Therefore, we maintain it on the xy plane. And then because it's a circle, we use cosine v instead of theta because we're using uv. But if you want to, you can do r theta. As a matter of fact, maybe I do that. That probably make it easier. And the domain R will go from 0 to A, because that's the radius of the circle. And theta, to form a complete circle, go from 0 to 2 pi. So to use the parameterization to form my line integral, I will need to form these cross products. So I'm going to go ahead and do that. So dg over dr would equal to cosine theta sine theta 0. And dg over d theta would equal to negative u sine theta u cosine theta 0. Oh, actually, you know what? Oh, I'm sorry, r. Actually, you know what? I just realized one thing. I do need this circle actually rotating in the opposite direction so that the normal vector point downward. So I'm going to have to negate both of these. So therefore, we'll negate both of these, and I would actually negate this. So now I have the correct orientation, because before the orientation of the circle would actually have the perpendicular vector point into the cylinder, which we cannot allow that because the problem specified is not. So what is the cross product between dg over dr and d theta over dr? So that cross product, once again, I'm going to just let you do that. But if you do that correctly, it actually will come out to be, So if you do it correctly, it should come out to be 0, 0, r, or 0, 0, negative r. I'm sorry, I keep on forgetting. Which actually makes sense, because you can see that the perpendicular vector n1 is pointing straight down. Okay? So if that's the case, now I can actually form my integral. So my integral would be over, I'm going to collectively call this my d, because that's my domain for my parameterization now. So I'm going to say double integral of d of vector f of g of r theta dot product, the cross product, and then dr d theta in this case, dg over dr cross dg over d theta, dr d theta. So that actually come out to be a double integral over d, negative r cosine theta, negative r sine theta, 0, dot product, 0, 0, negative r, dr d theta. Now, unfortunately, or maybe fortunately for us, actually, in this case, this dot product come out to be 0. And so, therefore, tell me that this entire integral just come out to be one big 0 for S1. So, therefore, now I can say that this double integral over S1, vector f dot d vector s, is actually equal to 0. So that one is easy. It come out to be 0. That's nice. We're going to do S2. So in this case, I would like you to actually take a minute to think about what should the parameterization be, because it's actually very similar to S1. So I would say you should pause the video and go and take a minute to think about it. And then unpause and see if you match what I have. And I'm going to just continue, of course. So for S2, I will also, because it's also just a circle, but the circle that completely fill in circle radius A and also what's inside. And in this one, we have to orient it using right hand rule so that the perpendicular vector point upward. So therefore, this one would actually be r cosine theta, r sine theta, but B, because this surface S2 is actually at the height of the cylinder. So therefore, the z coordinate should be equal to B. And in this case, our domain would mirror S1. R go from 0 to A, and theta go from 0 to 2 pi. And some of you might be thinking like, wait, doesn't when we use polar coordinates, don't we not let R equal to 0? You're correct. In a polar coordinate, we don't want to let R equal to 0 because it will make it not 1 to 1. But in here, it really doesn't matter because we're not doing a coordinate transformation. So if you want to put down just greater than 0, you're okay, because you basically be excluding the point 0, 0. Or the z-axis in this case, but it doesn't affect the surface integral, so it's up to you. Notice that this actually works out very similar to the partial derivative. It's actually exactly the same. Except that is, the negation is in the different spot. Because not negative r cosine theta, negative r sine theta. So therefore, it's just basically negation of the derivative that of the partial derivative we had before. And so the cross product in this case is come out to be 0, 0, positive r. So how does that change our integral? Well, let's find out. So here's my double integral of d of vector f of g of r theta dot product dg over dr cross dg over d theta dr d theta. So therefore in this case I'm going to say theta go from 0 to 2 pi, r go from 0 to a, and I'm going to have basically the dot product here, r cosine theta r sine theta b, dot product 0 0 r, and I have dr d theta. Okay, so if you look at this dot product right here, notice to choose 0 just basically make the first two terms go away, and I just have br as my integrand. So I can just simply integrate this relatively easy. So my first integration with r would give me 1/2 br squared. Evaluate from r equal to 0 to r equal to a d theta. So that just become, this just become 1/2 b, 1/2 a squared b, I guess. And if I integrate with d theta, since 1/2 a squared b is a constant, I'm going to pull that out and just integrate theta from 0 to 2 pi of d theta. And it shouldn't take you too long to figure out that that just equal to 2 pi. And so the 2 cancel the 1/2. Seems to me 1/2 is pi a squared b. All right, so that's S2. So S3 is probably the harder of the three, but it's not something that we cannot figure it out. So the key is once again try to figure out what is the parameterization. So in this case, it's the lateral surface area. So the top and the bottom are just basically the circle of radius A. But it has to go all the way from the XY plane up to where height B is. So in this case, the parameterization is actually equal to this. You know what? I'm going to use UV, I guess. I'm trying to think what would be... I guess I'm going to just use U here, and then V will be the bottom. It technically really doesn't matter which one you use, but I'm just going to use U as like theta, and then V is like the Z coordinates. In this case, U would go between 0 and 2 pi, because they have to form one complete circle. V is the Z coordinate, and the Z coordinate actually have to go from 0 up to B. So that would be my D in my integral using the parametric representation. And in this case, dg over du would actually equal to negative a sine u, a cosine u, and 0. And dg over dv would actually just equal to 0, 0, 1. And the cross product is actually wound up going to be a cosine u, a sine u 0, if I did it correctly. Okay, so now I'm ready to form my integral. So my integral for S3 would be this. Du dv. So that would be, I'm just going to go with, I don't know, I'm just going to go with v from 0 to b, u from 0 to 2 pi, and this is just a cosine u, a sine u, v. dot product a cosine u, a sine u, 0. And then I can't run a rumor because it's right underneath du dv. So if you look at this dot product, the dot product actually come out to be a squared cosine square u plus a squared sine square u plus 0, of course. And once again, it's not the first time we encountered this. I mean, the number of times we encountered this Pythagorean identity in the last couple videos is like almost every video we have like 10 times. So you should recognize that that come out to be just a squared. So therefore imply that our integral is just v go from 0 to b, u go from 0 to 2 pi of a squared du dv. And that you should be able to quickly figure out that the integral of this thing is 2 pi a squared b. So now we have a result. Now we can actually put all this together. So therefore, tell me that this double integral over s of vector f dot d vector s would equal to s1 plus s2 plus s3, the surface integral for each one. And some of you might be thinking, what's the difference between the s vector s and the s lowercase s1, s2, s3? The lowercase s, not the lowercase, but without the arrow, is the name of the surface. While this d vector s actually represent like the vector on that surface. So a little different. Okay, which is important that you pay attention to, because surprisingly in 9.4 we also go and talk about something called ds, but it's a scripted d, which is a partial derivative d, and also doesn't have the vector on top, and it represents something completely different. So it's very important that you try to make sure you understand the notation and don't get yourself all confused. So this just come out to be 0 plus pi a squared b plus 2 pi a squared b. So it seems to me that this integral come out to be 3 pi a squared b. So that seems pretty good. A lot of work to try to calculate this because it required the derivative, the gradient or the partial derivative, and then the cross product, and then the dot product, and then the integration twice to actually get down to the answers. Unless you run into this scenario where you're integrating 0, then that's easy. Now, I'm going to try to present to you a better way to calculate this. And in this scenario, it actually work out quite nicely because of it. So another way to actually use it is to actually bypass the parameterization and simply just use the normal vector to see if we can actually figure it out. So show you how that worked. So here's my surface, and we have surface 1, surface 2, and surface 3. What I want to do is actually identify what's the normal vector. So let's start with normal vector n1. So that vector is pointing straight down. As a matter of fact, we should already know that I can say is just 0, 0, -1. That would be the normal vector that pointing straight down. Notice that is a unit vector. That's what we need, the normal unit vector, because that's what we want to use in this notation. And 2, it should also be easy to identify. That should be 0, 0, positive 1, because it points straight up. The tricky one is the one in the middle. What is vector n3? So n3 is actually something that you also know. Why? Because I already explained it to you right in the beginning, if you pay attention. See, notice that when I give out this vector field f of xyz equal to xyz, I told you that this one is when you imagine you have an explosion, then everything gets pushed away from the origin. And when you think about it, that actually basically means that you actually have a when you have an explosion, imagine a shock wave that radiate out. It will actually form a surface of a sphere. And then this vector will point actually away from that surface, which basically means it's normal, perpendicular to the surface of the sphere. And this vector n3 would actually be same exact vector, except that it's just on the xy plane or parallel to xy plane. So this actually would come out to be this vector. Because n3 doesn't go up and down, it just basically radiates away from the circle. Okay, now however, there's a problem. The problem is that this is not a unit vector. I do have to divide it by its length. Now, and also, you actually know this is the normal vector also because we found that out from here. See? Right there. Oh, yeah, I know. That doesn't look like xy, does it? But if you think about it, it's an a cosine u, the x coordinates, a sine u, the y coordinate from g of uv. So, and lucky for us, because the length of a xy0 is just x squared plus y squared. And in this lateral area is actually formed by the circle on top and the bottom, where the circle has a radius of a. So this actually come out to be just this. Because x squared plus y squared equal to a squared. Okay, so let's talk about this. So this top part is x squared plus y squared equal to a squared, and z is equal to b. The bottom surface S1 will be x squared plus y squared equal to a squared. Well, that's the boundary of it. And then z equal to 0. And then this whole thing is height b. Don't forget. So now having the perpendicular vector actually allow me to quite easily calculate these three surface integral. So show you. So the surface integral is actually given by this. So I'm going to try to calculate the surface integral for S1. So our second notation is actually this. Oop, not theta, d sigma. And in this case, I'm going to bypass the parametric representation and just use x, y, and z. So this is my function vector f. For S1, our perpendicular vector is 0, 0, negative 1. And we have d sigma. So if I do go through this dot product actually come out to be just negative z. So therefore, this integral is just integral of S1 z, or negative z, d sigma. I don't like my sigma. There you go. But for S1, z is 0. So therefore, that come out to be just integral of S1 of 0 d sigma. And of course, that come out to be 0. And notice that is the exact result that we got from here. Now let's do the surface S2. So once again, I'm going to do vector f is just x, y, z. The normal vector for S2 is 0, 0, 1, d sigma. So what is this dot product come out to be? Well, just come out to be z. So therefore, it's just this integral of S2 of z d sigma. But for S2, z is a fixed value b. So therefore, meaning that it just becomes this. And since b is a constant, I'm going to pull that out. And now come the interesting part. We are basically doing a double integral of d sigma. What should that equal to? So if you look back in your notes, let's see if you can find it somewhere over here. You actually learn about it right in our first video, where if you integrate a region d sigma, you just basically get the area of that region. I just made a notation error here. I would say that should be an S. Okay. So make sure you fix that in your notes. So in this case, what I have would just basically be the area of S2, which area of S2 is a circle of radius a. So therefore will be a pi a squared. Notice that's the same exact result we have previously. And yes, I know it's past 30 minutes, but this is the last thing I'm going to show you. So how about S3? Well, same thing. So when I carry out this dot product right here, I will actually have x squared over a plus y squared over a. Now, if I combine them together, that becomes x squared plus y squared over a. And remember, in S3, x squared plus y squared is actually equal to a squared. So that just comes out to be a. So therefore, that means this just equal to a triple integral of S3 of a d sigma, which just like before, I'm going to pull out the a, and I just have this. And once again, what the double integral S3 d sigma represent? The area of S3. So that means is the area of S3, which is basically the lateral area of this cylinder. And if you hopefully remember the formula for that is 2 pi RH, which in this case 2 pi AB, and that comes out to be 2 pi A squared B. And so now I can say that the integral over S vector f dot d vector s, which is equal to 0 plus pi a squared b plus 2 pi a squared b. That comes out to be 3 pi a squared b, exactly what we found out before. So in this scenario, I can actually make use of the fact that we know the perpendicular vector. And in this scenario, in this particular example, all the integral just wind up being just finding the area of the surface that we are dealing with. So that makes the problem easier. Now, does that always happen? Obviously not. This is an example. So, but it does give you multiple ways to actually form this answer. As a matter of fact, when we get to 9.4, which is our next video, when we start 9.4, I will show you how to use the theorem that we're going to learn in 9.4 to actually calculate this without going through 3 separate integration of 3 separate surface integral. All right, but unfortunately, that will have to wait until next video. So at this point, I'm going to say that's it. This is truly the last video for 9.3. We'll start on next video on 9.4. Okay, I'll talk to you guys soon. Bye-bye.